This video is going to cover the independent sample z-test for proportions. So I think maybe the way uh, to introduce this is with an example. So let's say that I have a random sample of 500 people selected from some large metropolitan area, and I'm doing this to determine information about consumer behaviors. And so one of the questions that was asked on this survey was, do you intend to buy some product? And I'm kind of interested in whether there are differences across genders. So it turns out that among the 500 people that were included in this study, 240 were male, and of those, 136 said, yes, I'm interested in whatever product A is, while the remainder of my sample, so 260, were females, and 174 answered yes. So the question is whether there's evidence that there's a difference between males and females in terms of their preference for product A. So I went over to the piece of paper here and just summarized what we have. So I put the males in one column, females in the other. And the way to think about this is I have two different binomial experiments. You know, it's like I've got the male coin and I've got the female coin. I flip the male coin 240 times and I observe 136 heads where, you know, the coin comes up yes. I flipped the female coin 260 times and observed 174 heads. And what I'd like to know is whether the probability of a head for these two coins is equal. So let's just say that P1 is the true probability of a yes for males. And we're going to say P2 is the true probability of a yes for females. And so what I'm really interested in is the null hypothesis that P1 is exactly the same thing as P2. Now, I'd like to point out that this null hypothesis is completely equivalent to the null hypothesis that P1 minus P2 is equal to 0. And sometimes I'll call this difference between them D. So that's completely equivalent to testing the equality of these proportions. My alternative hypothesis is that P1 is not the same as P2, but that's exactly the same thing as saying this D is not equal to 0. All right, well, as we always do with hypothesis testing, we condition on the null and then evaluate the evidence against it. So let's just assume that H0 is true. And, in that case, i.e., the proportions are the same. So P1 is the same as P2. Now, what I'd like to do is evaluate how plausible this null hypothesis is given the evidence that I have. So I could go off and compute some percentages, and if I compute the percentage for males, it's about 57%, for females about 67%, and these look quite different. And so how plausible is it that the proportions would be equal when I've observed this evidence at hand? So let's go off and just form an estimate of how different they are. And I'm going to call this estimate of how different they are d hat. So d hat is going to be p hat 1 minus p hat 2, which in our case is going to be 136 over 240. So that's the proportion for males minus 174 over 260. And this is equal to about minus 0.10. If we go back to the course packet, I actually wrote it out for us, 0.1026. 0.1026 if you want a few more decimal places there. Now, what's important to note is that p hat 1 is approximately normal. And the reason we know that is because of the the normal approximation of the binomial. P hat 2 is also approximately normal. So if I compute the difference between two approximately normal things, I get something that's also approximately normal. So this is what my sampling distribution for d hat is going to look like. It's going to be normal, approximately normal, and under the null hypothesis, the mean of this is going to be 0. So why is that? Well, I assumed that these proportions were equal, which implies d is equal to 0. And if you want to go through a little bit of formality on this, the expected value of d hat would be the expected value of p hat 1 minus p hat 2. And this would be the expected value of p hat 1 minus the expected value of p hat 2. And under the null hypothesis, this is equal to p1 minus p2, but we've assumed these are the same under the null, so I'll just write this as under h naught. This is equal to p minus p, or 0. All right, so that's the kind of the long way for me to conclude that the difference is actually equal to 0. Now, the other thing we need to know is what is the variance of the sampling distribution? So we could call this the sampling distribution of the difference. So let's go find that the variance of this. So what is the variance of d hat? I actually worked this, must have been back during week 3 when we were talking about two random variables. It was a problem out of Devor. Well, this is just going to be the variance of p hat 1 minus p hat 2. And I have two independent samples, and so p hat 1 is independent of p hat 2. This is going to be equal to the variance of p hat 1. Now, this minus sign, think of this as a coefficient of -1 that gets squared when you bring it out of the variance operator. So it's -1 squared. So this becomes plus the variance of p hat 2. Now, what you have to remember is I'm just going to go write this over here. The variance of p hat sub j for group J. Remember from, this must have been week 4 when we did sampling distributions, is just going to be pj times 1 minus pj all over nj. So that's my the variance of a proportion, which is just follows from something we know from the binomial distribution. So this is going to be p1 times 1 minus p1 divided by n1 plus, well, p2, 1 minus p2 divided by n2. So none of what I've done so far uses the null hypothesis. So under the null, we've assumed that these p's are the same. So I'm just going to write this is equal to, under the null hypothesis, p times 1 minus p all over n1 plus, well, p times 1 minus p all over n2. And I can do a little bit of simplification on this by factoring out p times 1 minus p. And this is going to be 1 over n1 plus 1 over n2. So this should look a little bit like the formula we had for the independent sample t-test for means, where we had that 1 over n1 plus n over 1 over n2 times the variance, the pooled variance. So this is basically the same formula, except we have a special version of the variance here. Now we do one more thing we estimate a pooled proportion. So under the null hypothesis, the proportions are the same. So we're going to make a pooled estimate of P, which I'm going to call P hat, which in our case is just going to be the number of yeses from group 1 plus the number of yeses in group 2 divided by the total sample size. So here we're going to have, if we go back to what I just look at what I had before, we have 136 yeses for the men. We have 174, so 174 for the women. And remember, our total sample size was 500. So if we go back to the course packet, I'll just show you that I worked that out earlier, and it's 0.62. So we could find the standard error of the difference, which I'll just write as SD hat. This would be the standard error estimated from data. So what I've done up here is all in theory. This is simply going to be the square root of 0.62 times 1 minus 0.62, and then I have 1 over 240 plus 1 over 260. And so that's going to be the standard error of the difference. And you'll see I've actually worked that out in the course packet to be 0.04345. All right, so I just wrote that number there. Well, here's let's go back to my graph of the sampling distribution. So I've sampled 500 people, certain number from each of my groups, and I've observed that the difference is minus 0.1 something or other. So minus 0.1026 is my test statistic. That's what I've seen from the data. And the way we're going to evaluate this hypothesis is to look at the area in this tail. And so let's just do a little thought experiment on this. If the area in this tail is small, what that would say is, under the null hypothesis, the difference is 0, it would be very unlikely for me to observe two proportions that differed by this much or more. And therefore, I would call into question whether that difference is really 0. So this is the distribution under H naught. Instead, what I would assume is that the difference really comes from a different distribution. This would be the distribution under the alternative hypothesis, that the mean is something else. I don't mean it to be minus 0.1026, but the means are not, the proportions are not the same, and therefore the difference is not 0. All right. Alternatively, let's say we go find the area in this tail, and it's large. So if the area is large, what that is saying is we would observe a difference like minus 0.10 regularly if the null hypothesis is true. Therefore, there's nothing weird about the assumption that the difference is 0, and it's entirely plausible that the difference is 0. So everything hinges on us finding the area in that tail. So let's go do this. What's the probability that I observe a d hat less than minus 0.1026? Well, again, we've used the normal approximation of the binomial to make conclusions about the normality of p hat, our different p hats. So this can be approximately equal to the probability of me having a z less than minus 0.1026 minus the mean. So the mean in this case is 0. Now I need the standard deviation of that distribution. Well, I don't really know that, but I have a pretty good estimate of it with the standard error. So 0.04345. And this whole thing is called the t statistic, or z statistic in this case. And so you can see I actually computed that, 2.36. And we can go look this up with a normal table to find the area 0.0091. So I'm just going to go write that in next to this. So 0.0091. That's the area in that tail. Now, is that the p-value? The answer is no. The reason that's not the p-value is because you have to go look at your alternative hypothesis. So the alternative hypothesis is that the proportions are not equal. So before we looked at the data, we had no clue that the proportion for males was going to be smaller than that for females. Therefore, I need to account for a symmetrical tail on the other side that also has area 0.0091. So my ultimate p-value is going to equal 2 times 0.0091, and I can do that one in my head, 0.0182. And that p-value, if we're going to use the 5% cutoff level, is less than 5%, so we're going to reject H naught. So I always like to cross it out. Conclude that the proportion for men is less than the proportion for women. So at this point, I've looked at my data and ruled out sampling variation with this test, and therefore, the fact that this proportion for men was less than the proportion for women indicates to me that I can reject H naught. Now, another approach to this would be to form a 95% confidence interval. So let's go do that. The 95% confidence interval, basically I've got a normal random variable, approximately normal random variable, and I know it's standard error. So the 95% confidence interval would be something like this, minus 0.1026 plus or minus 1.96 times the standard error. So 0.04345. And I think I worked this out in the course packet. And so you'll see that this works out to be, I did the other side in the course packet, minus 0.017 to minus 0.19. So if we come back to the, I just wrote that out. And so the way I could use the confidence interval to test the hypothesis would be to take my reference value. So the reference value for the difference is 0. And see if that's contained in the confidence interval. So 0 is not in minus 0.017 through minus 0.19. So we're going to reject the possibility that D, which is equal to P1 minus P2, is equal to 0. So that's another way that we can do this hypothesis test. You can do that with the confidence intervals as opposed to the p-value, and that's equivalent to what we're doing here. All right. Another thing that I want to show is how to do this test in R. So let's go over to R, and there's a function here called prop.test, and we can go read the help page on this. Basically what we do is we give it a vector of counts of successes. So those would be my x's, and that's why R calls it x. And then I give a vector of n's as well. I can also specify whether I want a two-sided alternative or the less than or greater than if I want. And I can specify the confidence level for the p-value. There's another argument that I'm just going to mention, which is the continuity correction. What I've taught you off to the right does not use the continuity correction. But let's just go type this formula in. So remember, I had 136 yeses out of 240 among the males, 174 yeses out of 260 among the females, and then I say correct equals false to not use the continuity correction. And so what we see here, I'm just going to go bring up my document camera, and we're going to make this, show this what we had here. So what we see is that we have our two proportions down here, and those are the two proportions that I computed up here. Then what we did is we found the difference, and you'll see it doesn't give us the difference. It actually computes this with a chi-square distribution, which is an equivalent way of doing this. And you're going to notice you get exactly the same p-value. So my p-value was 0.0182, here it is. And they got 0.0182 using the chi-square distribution. And those two, again, are equivalent because a chi-square distribution with 1 degree of freedom is actually a standard normal squared. So if I took the test statistic they're using is slightly different, but equivalent. Now we could also use the continuity correction. So remember that we're approximating a discrete distribution with a continuous distribution, and so when we're doing finding probabilities of just a single binomial, we had to add 0.5 or subtract 0.5, and that would improve the the approximation of the normal distribution. So this is doing something very similar. We end up with something pretty close, 0.0233, and I suspect this answer is going to be closer to the correct value. There's actually some exact tests that we could do like the binomial, but we're not going to cover that in this class. We come to the same conclusion. They're both, to 1 decimal place equal. So minus 0.0182 rounds to 0.02, and this rounds to 0.02. So they're pretty close. They lead us to the same conclusion. I would trust the one with the continuity correction slightly more, but we're getting about the same answer. So that's an illustration of the z-test for the equality of two proportions coming from independent random samples.